Welcome to another week of chillers and HVAC. Oh man, so much time on the road. I appreciate everybody just being patient. I know I've had some trips here recently. I've got some more trips coming up, but it's the time of year. There's a lot of training, a lot of consulting, a lot of stuff going on. So um, I've got it'll be a couple of weeks before the next trip, but I will be in was it Kansas here in a couple of weeks. So yeah. Anyway, it'll be all right. We will figure it out. And I think the Kansas trip. Actually, I should be able to still do the stream that week because that's later in the week and it's a short trip. So I think I'll still be available for Monday. I did a poll. I posted it pretty late last night because it's something I've been thinking about. But I realized that it wasn't really that fair of a poll either in the end. So I'm thinking about maybe redoing it. I don't know that I will, but basically, I'm trying to get a feel for, you know, do I do a good enough job explaining the basics? I know I have a tendency to get really technical and dive off into the deep end of some of these topics, and in that process, it can be really hard for somebody who's unfamiliar to keep up. And I know that feeling. I remember that feeling, right? And I've been reminded of it recently because I've gotten more and more interested in like coding and stuff as like kind of a side hobby project, if you will, and just getting familiar with that. And man, like there's a lot to it. There's a whole structure, and depending on the language and all the stuff you get into, and listening to people just kind of talk about it as I get interested in it, um, it really, like, if they're coming in with an expectation that you already have some kind of background, most of the time, the folks that I have come across, that is kind of they're speaking to experienced people, and then trying to get the vocabulary that I just have no exposure to previously. Like, it reminded me very much of what it's like. Even though you've got HVAC training and you may understand some of the terms being used, there are so much of our conversations that really is very unique to the chiller side of it. And that's something that's really hard for those of us who have experience to try to keep perspective on and remember. And I'm realizing I think recently I've really fallen into that trap pretty deeply of just running off the rails with a particular topic. And for those of you who've been around, and I've gotten these comments where when you first started following and getting involved in the community, uh, it was hard to keep track of anything because what we're discussing is just so far outside of what you're used to hearing. You just don't understand the language we're speaking for the most part. Um, but you try, and you eventually, with enough time, you start to figure it out and enough research. But it makes getting started in that process very jarring. Um, and like, but you eventually figure it out, I guess is my point. And you kind of keep it going. But there's a lot of people who I know that they're really interested in this, but they feel so overwhelmed that they end up just not feeling like they're capable of understanding this, getting involved in it, and continuing their career forward. And even myself, like um, the first couple of videos and stuff of people programming I watch is like, man, this is way too far for me. Like, I don't know how I'm gonna grasp this, but I also have just kind of taken a more casual approach to it, and it's helped me take it less seriously, right? My point being, the poll was to kind of get a feel for where y'all are at and how I'm approaching what I'm explaining. Now, one of the mistakes I made with that poll is I didn't give a middle ground. I accidentally, because it was late and I was in a hurry, but it's just something fresh in my mind at the time. I ended up just splitting you to one extreme or the other. Either you thought, basically, I was way too advanced or I wasn't advanced enough. Um, and so my point, I really wanted to take an opportunity to take a step back a little bit better, do a better job at covering some of these fundamentals better, and not get so overly technical without the foundation. Right? I think that's the key thing there. Not taking it too far without the foundation first. If I'm going to get technical into something, at least give some kind of foundation, do better with these acronyms and stuff. Anyway, I'm going off on a little bit of a rant here. It's just something that's been on my mind, and I've personally got to feel those feelings again, trying to just have fun and explore new ideas and concepts. And it's been a good reminder. It's a reminder that I think I've needed. I see everybody in the chat. How you doing, everybody? Hope you're having a great Monday. If you're not, let me have the bad one for you. Does it sound like a deal? Let's do that. With that being said, I do see we got a couple of questions. Do you do anything with Frigil microgel microgel Frigil? No. Southern Comfort. Those things aren't ringing a bell to me. And if how you doing, Michael? I see you, bud. See, I do have. I see the Trane chiller economizer. We're gonna dive into that momentarily, and then I do have kind of a fun exercise that I want to get into today. Oh, that's not the right one. I was trying to figure out a chat thing. Okay, we're going to come over here to Google Maps today, and I'm going to show you something kind of fun. I did this the other day with one of the consults, and this is a strategy to kind of find something, or to, well, I'll talk about it later. Anyway, we're going to get involved in Google Maps here in a little bit, so just putting it out there. But first, let's get into this Trane economizer. All right, get it pulled up here. Ooh. Here, let me. Yeah, that'll work better. Okay. Trane chiller, economizer. Please explain. Absolutely. So the whole purpose of an economizer, let's start there really quick and I'll get into the whiteboard and we can kind of draw some of the refrigeration cycle around that. The whole purpose is to improve the overall efficiency of the chiller. And we can do that by making better use of our refrigerant to not only reduce some of the load on the compressor, but also we can improve our effectiveness of the refrigerant by reducing what we call enthalpy. Enthalpy is the actual heat content of our refrigerant or our material or fluid. So without getting crazy into enthalpy as a term, the point is it's just showing us the amount of heat that something contains. The economizer allows us to lower the enthalpy, which allows the refrigerant to be more effective. But it also allows us to reduce some load on the compressor. So let's get into some actual diagrams. And I'm sitting here debating, do I go whiteboard or do I go actual diagrams? I'm I've actually got, I'm going to go actual diagrams here because I've got some really good ones I like to use for this. Just give me just a second. I would much rather, and I've actually made some for the CVH. So we will use this one. And then there's another diagram of the actual Trane chiller refrigerant circuit. We're going to pull that one in here. Let me find the right one somewhere in this maze of crap I've saved. Where'd you go? Oh, come on. I've got it in here. Just give me 1 second. I could draw it if I really needed to, but I feel Trane has some really good diagrams. Here, we're going to do, come over here. Maybe I've got it in this folder. I don't. The heck? Okay, all right. Well, we're just going to whiteboard that part then. All right, so this here is part of our enthalpy chart. Okay, we'll come back to this. All right, I'm not going to spend a ton of time on it. We don't need to. This is just going to kind of give you an idea. Now, being the fact that you said it was a Trane chiller with an economizer, I'm going to assume you're referring to a Trane CV series. We're going to go with, say, a CVH. This will be true for an E or an F. This particular schematic is true for an F. Now, I'm just talking about the model of the chiller. So when you look at the model number, the first few letters, for Trane specifically, is going to be the first 4 that you're going to look at. You're going to see CV, and then it could be, it could be a CD. Either way, this is Centrifugal, and I forget what the rest of it stands for with Trane, but anyway, these are their basic models. All right, so if you have a CV or CD series with an economizer, this is going to be something that is kind of a basic concept we're going to follow. Now, from a refrigerant perspective, let's draw that. So let's continue with the CVHF perspective. The CVHF has 2 impellers instead of 3. Some of the others, like a E or a G, would have, which is the last letter of the model number, all right? Or not the model, the last of the 4 first digits, okay? So we have CDHF, CDHG, and then we have a CVHE, CVHF, and it's not just that, but just to kind of give you a high level. We're gonna stick with the CVHFs for a simpler. So we have an impeller, and then we have our next impeller. Oh yeah, getting a little excited there. We're going to put this inside the compressor. Okay, here's our nose cone. Come down into our evaporator. And then we're going to have our actual economizer. So we're going to call this the econ. And then coming out of our discharge, I'm just going to draw this as a pipe up here. Very crude schematic, but you'll get the general idea. This is our condenser. And then our drop leg comes out into our economizer. Then we have another leg coming out into our evaporator. Guide vanes here. All right, so this particular one is just going to have a single pipe coming up right here. So everything's going to flow. Let me get some color involved here so you kind of see the process. So we're going to have low pressure. Purple is going to be our medium pressure. And we've actually got 2 medium pressures here. Let's see. Well, this one doesn't have an internal. So what? Yeah, this will work. This will work. Going to be purple here. Right here is going to be low. And then we're going to do red for our high pressure. Oh, that red gets us every time. So freaking loud. Here's a red. High pressure, high pressure. And then here in the compressor, we have medium pressure coming in. So low pressure coming in, medium pressure. This is the basic refrigeration cycle for our Trane CVH series, or CDH. Okay, now this specifically have 2 impellers, so this is going to be our F series in this lineup. Gotta get my coffee hit. Now, what's happening here? The evaporator is going to function the same. This is a flooded style of evaporator. Refrigerant's going to sit over the tubes. It's going to boil off. Vapor, superheated vapor, comes back into the first stage impeller. Okay, so this is going to be first and then second. So it's a multi-stage design compressor on these. This is very important. Okay, this is not specific to just Trane. Trane is not the only company that does this. But it's important to understand that to make this work correctly, we need a multi-stage compressor. If it was just one impeller, single stage, this same concept wouldn't work exactly the same. So we have superheated vapor coming off. Now this vapor is going to be 0.5 degree Fahrenheit, 1 degree Fahrenheit, superheated coming into our compressor. It sounds really low, but this is normal for centrifugals. We've got a set of guide vanes right here. These guide vanes are controlling the refrigerant flow coming into the front of the impeller. If you haven't seen an impeller before, yes, I have one on my wall right here. So this is a very small impeller. Okay, this is not what you'd find in a Trane, but this comes out of a turbo core. But it's the same basic design concept that you would find in the Trane. The impeller it's just going to be bigger, larger scale, but for the most part, the same basic design on the impeller itself. So there's a physical representation of what an impeller actually looks like. You can kind of picture that inside of here. So we've got a set of vanes that are basically just paddles that are controlling the refrigerant coming in. This impeller takes our refrigerant to a medium pressure. So we go from low pressure to medium pressure. That medium pressure then gets fed into the second impeller, which goes from medium to high pressure. So it's a 2-stage cycle on this. If the 3 impeller designs for these, where there's 3 of them, we just go from a medium or a low pressure to medium low to medium high, and then medium high to high pressure. So that's your staging sequence for a 3-stage versus 2-stage machine. So out of here we come high pressure refrigerant. Right? Now these are low pressure machines. What I mean by that, they operate in a vacuum, especially in the evaporator, but the refrigerant as a whole will operate down into a vacuum. So they will be below positive pressure. So that's very important to keep in mind with this style of machine. It doesn't really affect much of anything other than just be aware of the type of refrigerant. Anyway, discharge gas comes into the condenser. Condenser condenses the discharge gas accordingly. So these are both water-cooled heat exchangers, condenser and evaporator. These particular condensers generate a very minimal amount of subcooling. Basically, it's just enough subcooling to essentially ensure that we have a full column of liquid coming into our drop leg. So the drop leg, or the liquid line, is the line leaving the bottom of the condenser. When we come down out of this line, so we're still a high pressure liquid refrigerant, so high pressure superheated discharge gas, high pressure slightly subcooled liquid refrigerant. We come into a flash plate. It's just a fixed orifice, right? Just like with a little split system heat pump with a little orifice in there, something like that. This is just that on a much larger scale. It's actually a perforated plate, so it's just one steel plate with a bunch of tiny little measured, engineered pinholes in it that creates a pressure drop for us. But once we go through this first stage of pressure drop, we're not actually going into a low pressure state that the evaporator needs. We're going into a medium pressure. And this medium pressure, what that does is it creates the flash off effect, right? So we're familiar with the fact of TXV as an example. We go through that TXV and we're roughly 80-ish% liquid coming out of it, and that other 20-ish% vapor coming out of the TXV or the metering device, right? That's very standard procedure whenever we go from a high pressure to a low pressure state. We're going to have some flash gas in the process. That flash gas reduces efficiency. It reduces our enthalpy, or our ability to take in more heat. It keeps a higher enthalpy than what we want to have. So what we do, we have liquid, or that liquid refrigerant doesn't change in subcooling value. Okay, this is all liquid in here. Liquid refrigerant will stay in the bottom, but our vapor, the flash gas itself, will rise to the top of this chamber. Okay, this is just a big hunk or this is a big cylinder on the side of the chiller, right, with the economizer. So you're very specific to calling out the economizer in that process. That is what this is right here. The big, usually it'll be fully insulated and everything else. So we have our first stage of pressure drop. We have our 80% liquid stays here in this in a medium pressure state. That medium pressure vapor rises to the top of this chamber, and there is a pipe on the top of that then feeds up into the compressor. Now, if this was a 3-stage machine, not trying to confuse this, but just for clarity, if this was a 3-stage, you would see 2 pipes up here. Being that this is only a 2-stage compressor with a CVHF, which is our example, you will see just 1 pipe. And that's one really quick way to determine on these chillers. Do I have a 3-stage compressor or a 2-stage compressor? How many pipes are on the economizer? That will immediately tell you what you need to know. And just in case it helps, we're going to say CVHF. Just so that we're fully on the same page. This gets confusing really quickly if we're not careful, so I want to be very cautious of that. Okay, so what happens from here? So we've got this standing liquid here in the bottom of the economizer. We've got this vapor, which I show goes back up into the impeller. 2 things are happening in this process. Let's show both of them. On one hand, we are reducing the load on the compressor because this vapor gets drawn up into the 2nd stage impeller, where we have also a medium pressure state coming in from the 1st stage. So these 2 refrigerant streams mix right here, and they enter into the final, or the 2nd stage impeller, and then get turned into hot gas. Now, a big part of the work that our compressor has to do is compressing the refrigerant from its lower pressure state to its higher pressure state. All right, this is true for any compressor, scroll compressors. The higher your compression ratio, the more energy you're having to use to make that compression. Same thing is true here. What we've essentially done is we have began to reduce that compression ratio because we have introduced a medium pressure vapor back into the refrigerant stream part way into the cycle. The reason that reduces it is because we're not trying to go from low pressure to high pressure now with all of this vapor. Now all we have to do is get this medium pressure to high pressure. It has way less pressure rise necessary to still achieve a high pressure state. And because of that very fact, we're only going from medium to high pressure. The compressor has to put less work, less horsepower into this refrigerant than it would have had to do if all of that vapor went all the way back in through the suction as a low pressure. This is the fundamental purpose of that economizer, is we are reducing compressor load by not having the compressor cycle 100% of the charge as low pressure gas back to a high pressure. We can take some of that as medium pressure, step it up to high pressure, reduce the total work the compressor has to do in the end. Now, that's not the only thing being accomplished here. This is just one side of it. The other piece of this is in the liquid refrigerant that's left, and that's where we get into our enthalpy chart. So this is a basic saturation chart curve. All right, there's nothing fancy going on here. What I've got is condenser pressure, my CP, my medium pressure, which is my MP, and my evaporator pressure, which is EP. That's what I'm establishing here. So this is my pressure on the chart. This is the actual enthalpy. Remember, enthalpy is just is referencing heat content. So the further to the left we are on this chart, the more room we have to take in heat. And the further to the right we are, the less room we have to take in heat. That is the basic fundamental, and the higher we are on this chart, the higher the pressure we are. The lower we are, the lower the pressure. This white line shows the saturation curve that our refrigerant is operating within. This is a basic enthalpy chart. When you see a saturation chart or for refrigerants, you see these curves. This is what it's showing you. It's showing you the enthalpy cycle of that refrigerant, or the saturation cycle. Now, let me explain what's happening here so that we get a concept of where we are. Our liquid refrigerant, as we come in, so I tell you, let's start with point number 1. Okay, I think that will be easier to follow. So on point number 1, we are right here in the evaporator. All right, so we've gotten into the evaporator. We're actually here at the suction line, and we're returning back to the compressor. So this is point number 1. So as we go from point 1, and we've entered the suction of the compressor, and up right here we are at the compressor discharge. All right, so we have raised that compressor, or that refrigerant pressure, and we have raised its saturation. From here, we have now gone through the compressor, and we're back over here. So this was our point 1. Over here would be our point 2. Then we send that refrigerant into the condenser to point 3. So this process is when we're right here, this line, this is processing through the condenser. So we're not lowering pressure, but we're removing heat from the refrigerant. So right here, from 1 to 2, this 2 is slightly over from 1 because this is the heat the compressor put into the refrigerant. All right, so this is heat of compression. All right, that's why it's not perfectly above it. But when we go into the condenser, we're not lowering pressure in the condenser. We're just removing heat. So from 2 to 3, this is where we're processing through the condenser. So this would be point number 2. We go through the condenser, we're at point number 3. That is when we're going from a liquid, or a hot gas into a liquid, right here. So we're at the liquid side of this curve. This is our gas side, this is our liquid side. Everything in between is an intermediate state. We're between a vapor and liquid. All right, so number 3, we're leaving the condenser, and we hit that first flash plate going into the economizer, and we have a split right here. This split is where the economizer's job is done. So from 4 to 5, 5 is the liquid that's left in the bottom of the economizer. From 4 to 7 is the vapor that gets sent back to the compressor and adds to that heat that you see at point 2. So this is our economizer line getting sent back to the compressor. Okay, this is where it gets blended. If you notice, even though if we had like several degrees of subcooling, let's say 10 degrees of subcooling, like some machines run, we would be over here. The fact is, though, we're not. We're right here on that saturation curve line, which means that we're maintaining a fully liquid state, but we're right at that fully liquid point, right? So we're not going into heavy subcooling like some machines like to run at. So that's what you're seeing here. The economizer, by removing that flash gas has removed all of this heat right here between 4 and 5. That heat that was here goes right here with that flash gas. And that is part of what this flash gas here is doing. It is carrying that heat away so that we have a lower enthalpy. And that's what this chart is showing you, is our enthalpy reduced. Our pressure didn't. Our enthalpy did. So now this liquid refrigerant can now handle a lot more heat to be put into it than it could have handled if we didn't send it through the economizer. Because if we would have gone straight from high pressure liquid to low pressure on the evaporator, you'll see how much further over to the right we are in our heat curve. So by doing this, we dramatically improve how much heat the liquid refrigerant can take in. So from 5 to 6, this is the next flash plate we go into, which is right over here. So these machines actually have a dual plate coming into the evaporator. It's about how the machine manages different load states and low load versus high load and maintaining efficiency, yada yada. Point is, there's two here. So you'll go through both of these plates, and then once we go medium pressure liquid to a low pressure liquid on the other side of those plates. And these two plates finish that pressure reduction process to get us to a low pressure saturation so that we can take in heat. Because remember, our saturation is there just for taking in heat and rejecting heat. That's the whole point of why we have the saturation we do. We need it below our water temperature to take in heat. We need it higher than our water temperature to let go of the heat. That's our very fundamental refrigeration process. It's the same thing as what we'd have with air. We're just doing it with water in this case instead of air. So as we come through this line, we are now into this 6-to-1 stage, which this is our superheating stage. So we're going from a saturated liquid refrigerant, low pressure, or at evaporator pressure, and we're flowing up to our point 1, which we're back to our suction line coming into the compressor once we hit this point. And the whole cycle starts over again. So this is the second part of what the economizer is doing inside of a Trane compressor, or in a Trane CVH refrigerant circuit. Reduces compressor load by recycling some of that medium pressure vapor, but also improves our enthalpy going into the evaporator, giving us better heat content. These two things together make a very effective machine. So that is the basic process of a Trane water-cooled centrifugal with the economizer. It is a lot. If it's not something you're familiar with, it's okay. This is where just taking time to read more material on it, get more familiar with it. This is something I go through multiple times and in detail inside of my certification course at chilleracademy.com. So if that's something you're interested in doing, I would encourage you to go there. We can discuss things further. There's a lot of other questions people have had around these same topics. You can read through their questions in the lesson comments. All that information is there if you need it any further. But just from it all bundled up in one high-level perspective, that is how that machine is functioning and why the economizer exists. The economizer does get slightly more complicated because it adds another layer of pressure drop inside of the economizer. We don't need to do that today, but that is the that's just kind of taking it to another level. That's what you'll see with a 3-stage machine versus 2-stage, right? The 2-stage is the simplest version of this. We're just going to stick to that for now. All right, amazing question, by the way. Absolutely love it. Let me catch up on the chat here real quick. How you doing, everybody? Hope you're having a great start to your week. For injection molding process cooling. Yes, used for injection molding. I've never seen one, but they look neat. I see there, Justice. Dunham Bush, Hercules series. Centrifugal doesn't get to full load. Compressor 100%, but IGV 23% open, even though it has a huge thermal load requirement. What to do to get the IGV open? So Justice, that's usually when I see it like that, most of these machines, the first goal for that stage is to reduce compressor speed as much as possible and open the IGV as much as possible. That is the standard staging sequence for a machine like that. When I see them where they're not wanting to open the IGV, but yet the compressor is ramping, that's because it's because it is sensing a surge state of some kind and it's trying to keep itself out of surging. Now I think you're giving some extra details here, so I can read through those here in a second. But just from an immediate high level, when I see that, that's what I'm looking at. It says, okay, so by running a high motor speed, I'm maximizing the amount of lift velocity I'm putting on the refrigerant, but I'm also trying to control how much volume goes through there. So I want to give that refrigerant as much punch as I can, if you will, while also trying to make sure I don't overload the diffuser and cause more surging to happen by allowing the IGVs to be open too far. So it's a delicate balance that I'm going between in that condition. So that's my first very high level thought, without having any other details. We'll catch up on it here in a second. At least once a week. It can be a little difficult. Yeah, and on that Southern Comfort, yeah, that particular setup I'm not familiar with, to be honest. I'm reading your chat with Michael here, and I don't think I've seen that specific setup. At least they can be a little difficult. Let's see. How's your suction pressure? So, yeah, Michael's already on it. Good job, bud. What compressor type? So Dunham Bush uses, the DCL CD. That DCL. Dunham Bush has two lines. They have one line that is turbo core, and they have one line of centrifugal that uses, basically it's the Carrier 19XR compressor. It's like carbon copy of the 19XR as far as I can tell. So I don't remember which of those the Hercules series is with the DCL, which you may answer that here. And it should be a 134 machine. Yeah, KP. Oh, come on, Michael. We gotta get international here, bud. We can convert these numbers. Come on, man. There we go. So I think 36 and 108. I gotta give Michael a hard time, guys. Sorry. Where's your condenser temps? That's a little bit high. Yeah, EFAP pressure seems normal. Guess condenser pressure isn't too high. Wonder what your approach is. Yeah. Michael's on the right track here, guys. Need all the info. Yep. He is absolutely on the right track. Evaporator 36, 110, 2-stage. Oh, see, two stage. Yeah. It's not. So 2-stage would be the turbo core then, right? Yeah, because I think that compressor they have is only a single. Man, I have to go back and look that up. Here in the moment, I'm questioning myself. Plugged into a slider. Google that machine. Yeah, okay, yeah, exactly. All right, so you confirmed it. That's basically Dunham Bush's version of the 19XR. Yeah, okay. All right, so now we're on the same page of what machine we're looking at. Water inlet around 84, outlet 93. So by approach is okay, do you mean the approach is less than 3 degrees on both barrels? That is something we want to be specific on. Inlet, outlet. So 84 inlet. Sounds fine. Which I guess I could convert that. 110 PSI. I don't have... So I don't do the whole PSI pressures thing. Let me pull up and watch what I'm doing here. Let me pull up my ref tool app. 134, 110. 134. 110. So that's 93 degrees. Okay, yeah. So your approach is literally on par. So okay, well that's kind of weird then. You said you've got a high load, but our condenser approach is shockingly low. To be honest, like normally, I would expect a slightly higher approach value for for having a load, right? It's normal to get 2 degrees, 2.5 degrees, something like that when under load. So it doesn't mean it's a problem. It just stands out to me as, oh, that's interesting. Keep reading here. Suction line, our outlet to the evaporator. Suction line is outlet from the evaporator. XLR. Yeah, if your suction line coming into the compressor, that is leaving the evaporator. Evaporator, inlet, outlet. $55, $46. Condenser. I see what you mean. Yeah, you've got to, assuming it's a 10-degree machine. Yeah, less than 2. New chiller's working less than 2 months. Rotation speed. Current draw. Current draw is low, around, yeah, right. Well, your IGV is pretty closed off. Yeah, thank you. There you gone. These are great shirts. It's actually one of my favorite shirts Navic has done. I think this was one of their HVAC tactical collaborations they did at AHR one year. This one is the when they did launch their pipe cutter series. It's a great shirt. Sounds like it's working fine. That compressor is variable speed. Well, you said it's not variable speed. No, it's not variable speed. 2-stage centrifugal has IGV hot gas bypass. Yeah, fixed speed, don't regulate, right. Yeah. Well, yeah, it sounds like it's doing great. Let me go back to the original. Doesn't get to full load. Compressor. Huge thermal. Before I give my response, I'm just trying to think through. I want to make sure. Do you mind confirm? Well, your hot gas bypass is going to be closed. You don't have the conditions that it would be open in the first place. So if it was open, that would be a problem. But even if it was open, we would see a higher IGV to achieve the numbers you do. Like there's no way that valve is open. So 46, 55, 84, 93. Yeah, Justice, it sounds like she's running great. Current draw is low, right? I mean, well, that's the thing, it's okay. This is actually a really good point that we should talk about. I'm glad this came up. It's a really good point. And this gets confusing, right? So, with a lot of machines, we're used to the concept that our load device needs to be at maximum to be fully staged. And Justice, if there's something we're not seeing here, please feel free, like, fill us in. But I'm with Mike here, Frylock. That it sounds like she's running great. I don't see being a because it is constant speed. It's the only means of load control it has is the IGV. Okay, let me get back to my point. A machine does not need to be at I'll give you the full data in your email. Well, it's okay. So this is an important concept, even if you have a grasp of it on your side. This is a great conversation. Like you're this is great. These are the kind of conversations that I want to have here. Like this is really good for everybody. And if you're already familiar with this, I apologize, but I think there's a lot of people who aren't. So we're used to when a scroll machine, we're going to take it back to that. When a scroll machine is fully loaded and you're processing at maximum load, what do you have happen? Every compressor is on, every one of them. And so that's the staging concept we get in our minds is, okay, well, for me to be at full capacity, then all compressors are online and I'm running at maximum this machine can do. And it can get confusing when we get into a screw machine, a screw compressor, because the vast majority of machines out there, we don't actually monitor slide position. Now, we might have just a variable speed only, like a York screw, which at that point we can monitor the physical hertz, the speed of the motor, and we can see the motor speed is at 200 hertz, a maximum hertz or not. So we can track that, but most screws out there are a slide, and we do not monitor that slide position. Something to be aware of. Most of the time, a screw compressor may be at full load state, but the actual slide not be at its maximum position. Now, when I say full load on the compressor, what I'm actually saying is full load on the motor. So because our motor load to turn that screw is at 100% RLA or FLA, it's at maximum current draw, that we're going to allow it to pull safely before it gets into a damaging state. That's what we call 100% on the compressor. It's 100% loaded. But in reality, if we actually allowed that slide inside of that compressor, which again, yes, I have one on the wall. I'll show you. Right here. If we actually allowed this slide to move to a 100% state, we would overamp the motor and force it to shut down. So it's not that the compressor is at a capacity. It is that where our motor is at capacity in a screw. So that's an important concept to get your head around, because the screw bolts would sit right here, and this is out of a Trane screw compressor, and it just slides back and forth. That's how we control capacity on a compressor like that. Now, with a centrifugal, we have a similar concept, except centrifugals don't play by all the same rules that everything else does, because they're not a positive displacement compressor. They're not forcing and compressing the refrigerant the same way. And it comes back to how good of a job, one, how good of a design is the compressor? How well is it charged? How well is it tuned? How well is it balanced? You can have a scenario like that where you've got really good water temperatures. You really do. You've got really good water temperatures for that machine, and it just doesn't need the full IGV. It's a good thing, because with the question I would have is, what controls the IGV? If you have a constant speed motor that just turns off and on, what controls the position of the IGV? The answer is the leaving water temperature. Just like what controls our compressor staging on an RTU. Leaving air temperature, supply air temperature, SAT. So our leaving water temperature, SLWT, with a compressor or a chiller, that is what our chilled water set point inside of the chiller is controlling to. Now, in our centrifugals case, the inlet guide vane, the IGV, is the device that is going to control how much refrigerant moves through that machine. If we're making set point, so if you've got a 46-degree set point, which my assumption is that is accurate, but given your load conditions, like you've got amazing approach values, you've got really good water values, you've got a great load, your condenser water is in a really nice sweet spot for a lot of those styles of machines. 84 degrees entering water, like sure, it could be lower, but honestly it's great. You could push that water probably a lot higher and still be okay for your particular conditions right now at a full load. All you need is 23% inlet guide vane. And because of just the way the machine is built, it's possible that it may be slightly oversized. That's another factor to consider here. It might be slightly oversized. Or maybe your evaporator loop is slightly slow on the water GPM, which it still may be within tolerance. Maybe that DP across that evaporator is slightly lower than what it may be rated for. You may notice that you bring that evaporator DP up, you get more flow through that barrel, and it starts putting a little more load than you already have on it. But you can see that if it was truly just an evaporator flow, you'd have great DP on your evaporator, but your condenser, you'd have a great temperature split. A great temperature split on your evaporator, but your condenser temperature split would be much lower. So you may have 10 degrees on the evap, but 5 or 6 degrees on the condenser. That could be an indication that while the evaporator looks like it has a lot of load, it's not actually moving that much heat through the machine. Whereas in your case, you've got a 9 degree and 9 degree. They're matching, which is great. So the fact that those two match each other, that your temperature difference across both barrels are that similar, tells you that they're both moving a relatively the same amount of heat, which would indicate to me that they likely are okay. Now maybe there's low flow. Maybe. Let me circle back to the low flow thing in a second. Let me finish the first thought. Realistically, that machine may only need a 23% inlet guide vane position to effectively and efficiently get to that set point. And as long as you're maintaining set point, that IGV is going to stay in that position. That is its job and its goal. It is to get to leaving water set point. Its entire life's mission is leaving water set point, and it will open and close that IGV accordingly. The only thing that'll change that is if we tried to go into a surge. Now, for anybody that's not familiar with surge, don't worry about it. It's a topic for another time. But surging is one of the few conditions that will cause the will cause the inlet guide vanes to close off. That's what they'll do. They'll close off to try to stop the surge. But at that point, you've lost control of the load, which, based off of your conditions, if those are stable where you said they were, that's not happening. And we're not hearing a surging state. We're not losing control of it. Okay, you said it's not running good. It doesn't meet the requirement. It needs to reach. All right, so now we're getting somewhere. Okay, this is great. Like I said, there's a lot of information we don't have. I know it's a lot to put into a chat. Let's see, in the evaporator. Yes, we need to get down to 38. Okay, all right. So we're getting somewhere. All right, this is good. Justice, if you have time and patience, I know it's kind of a pain to do it in a chat here. I'm happy to follow up via email after this and discuss it further. But if you have, I'd love to continue the conversation here. Like, these are always really fun. Anyway, to finish my thought, we need to. The compressor may not need to go above that. There are conditions that you have shared where the inlet guide vane does not actually have to open overly that far. Okay. So now getting back to the flow concern. If there is a low flow condition, low flow will cause the high temperature splits without actually causing, without actually moving that much heat. There we go. So low flow will cause high temperature differentials across your barrels without actually moving very much heat. Now, there could be a condition where both barrels are having a low flow state. Now, not to your specific thing, right? You already said we have a 38-degree set point. We're not getting there. So I'm talking about something different at the moment. I'm going to try not to scroll too hard because I know it gets really tangled really fast. Anyway, low flow can cause a high TD. So if you are concerned that it looks like the chiller is not staging up correctly, but you have a low flow state, that may be why. And if you fix the flow conditions, then you may see it start to stage up and everything run just fine beyond that, and you're good. So if we were to going in the context of you were leaving water set point, but the chiller looked like it had very little current draw and little IGV, that would be the only real concern I would have at that moment is, okay, am I having a low flow condition? And that could artificially create these numbers. Now, getting to your actual scenario, we have we need to get to 38. We're not. Yeah, you said flow is okay. We're measured it 2 to 3 times. It's good. Yeah. I get that. I'm not trying to push that on your specific thing. And I don't mean for this to be frustrating at all. Let's see. It needs to reach 38. So this is where I could argue, okay, are we dealing with a high flow condition? But that's the thing, is even if we had a high flow, so a high GPM, I would expect the machine, so usually I would expect the machine to really try to load up. So to your point, right, to the point you're making, we are way above set point. Like I said, IGV's goal in a scenario like this, get to set point. We want that leaving water at 38. We're only at 46. Why? Could there be... I'm going to assume it's maintaining stable there, and it's not in a pull down. Yeah, I'm gonna have to assume it's probably not in a pull down state. What is the lowest leaving water? Maybe something in the chiller settings preventing it from going that low. I mean, there could be. We know it's not a current limit because we've already established our current is really low. Right now we're at a high load state. So, okay, well, even still, what would you say? How much was that? What is our actual, see, 55 amps. What is our actual current limit set point right now? That may be one thing that could help us. Because there are some control panels, and that Dunham Bush should be using an MCS panel. There are some control panels that you can program them that once you get above a certain temperature range, it will automatically go into a pull down condition. We have parallel 3 chillers. 2 chillers are loading up. They meet the set point, but only this one is not opening the IGV. Usually, right, okay, that makes a lot of sense. All right, so we've got 2 on site. We have a data set that we're familiar with, right? So we know we've got 2 chillers that are doing what we want them to. The third one is not. That's really important, right? For everybody that's new to this, that's a really important metric. If you have machines on site that are functioning somewhat correctly, they are a very useful tool to help you contrast what's actually happening to your machine against and looking at, okay, what is different. So Justice, are there any status codes or anything on the display? I'm assuming you're logging in with a laptop on the MCS side of the system. You don't have to necessarily. They do have a fairly, well, it's not the world's greatest panel to thumb through, but okay, so it does periodically surge. Okay, so that periodic surging, yes, I'm assuming that periodic surging could be a really key indicator, because if it depends on how frequent, see, and that's one thing to keep in mind. Sometimes the chiller may trigger a surge in the control panel, and it technically may have had one, but it may not be audible for us to hear. So, and I've had this bite me hard before, where the controls was actually triggering a surge fault, and I didn't notice it. And it was just real quick on the display because it'd come in and out, but all it takes is that little blip, and it starts this staging cycle timer to where, okay, I'm going to back off, I'm going to let everything settle, I'm going to try to ease back into it, I'm going to back off, settle, ease into it, right? It gets in this whole back and forth tug and pull state. It's annoying as hell. So that's a really good catch, right? Surge on a machine like that. I mean, honestly, dude, it takes you back to, were those machines charged on site, or were they, because you said this was a new startup here recently, these are new machines, so were those charged at the factory or charged on site? Just one of the questions we have to question at that point is, okay, could there be a charge issue? Seem to get stuck in a low pressure hold and not be able to get out of it due to undercharge. Yes, and so if we have say a constant speed, that low of an IGV is going to cause a pretty high discharge superheat with that constant speed. So it's going to be hard to see on-site charge. Okay, so we are very confident in the charge then. So we can eliminate the charge issue. We're going to figure this out. Let's do this. All right, we had 3 out of 3 Dunham Bush chillers end up springing leaks within a year. They were turbo core. So why else would we occasionally surge? We don't have a high lift. Our lift is fine. I see some other questions coming in for other topics. We still have some time. I'll get to those right now. So for everybody that may be just joining, we're working on a DCL by Dunham Bush. This is basically it's Dunham Bush's version of the 19XR from Carrier. I've actually called that out with them before in their training class. I was like, dude, you know that's just a 19XR, right? They didn't really have a comment. They just kind of smiled back. But uh, anyway, in all fairness, I think Dunham Bush fixed the things that were wrong with the 19XR. There was a lot of things I didn't like about them, and Dunham Bush did it better, in my opinion. But you need info. I will. Okay. Well, it's the thing, Justice. You're not wasting our time. I really appreciate it, and I know you're kind of on the spot trying to feed us, and we're just going wild with the spitball ideas. What we may do, let's do this. We can put a pin in this for now. We've got a really interesting scenario going on. Next week, let's see if we can work through this on the side. And then I may do a follow-up next week and do a review of this ticket if that's okay with you, Justice. I don't have to do that. It's your personal site, your chiller, so it's up to you. But if everything's good, we may do a follow-up, and I may kind of walk through, okay, what we found, what we discussed, and maybe some of the adjustments we had to make, what was standing out to us, right? This may be a really good case study to do a follow-up with and talk through on stream. So either way, love the chat. That was really fun. Yeah, good times. We will provide some kind of conclusion to this, everybody. I know there's a lot of people on the edge of their seats right now. I know I am. All right, let's see. Okay, well, there's a couple of questions. I do want to do something kind of fun, though. I'm not going to make the... so I did verify. We're going to switch over to the desktop here, but I need to get the chat pulled up here, so just 1 second. So that way I can actually see. Live chat. All messages. Okay. Now I can see the chat this time. That way if something goes wrong and y'all are screaming at me, I know it. Because when I toggle over to the other screen, I won't be able to see anything. But let's do something fun. All right. So something I've heard frequently is, oh, well, there's just not that many chillers in my area. These are from even just companies who are interested in getting into the chiller space. They want to get involved. They want to see how they can have their part in it. And they're just not familiar with how to do this. So I want to actually kind of go through this process of, you want to get into chillers, you want to learn chillers, and you want to, but maybe you're not confident. Because there's somebody I worked with recently that it really felt like there were a very small chiller market in their area, even though they were in a major city. And it was just astounding to me that was true. So I finally, at lunch one day, said, you know what? I'm going to show you this. This is actually something I've done before to find chiller accounts. So I'm not familiar, so I'm in Texas. I'm based out of Austin and San Antonio. That's my service area that I've ran for years. But I'm not familiar with Dallas. All right. I've been to Dallas plenty of times. So I've never worked in Dallas as a contractor. So I don't really know what or where I'm looking at. And that's something I want to preface here. So I don't have a on-site advantage. But what I'm going to do is I'm going to toggle this over to the satellite view. And go away. We can even start with just kind of downtown here. So what are some things that separate an art a different types of equipment, right? And the answer to that is the actual condenser fans of this. So if you don't think there's a lot of chiller opportunities in your area, let's come do this. Let's identify some. So this is a Chase Bank building. We can see a high rise, Dallas Petroleum Club. So very, very fancy building. But we can see we have a penthouse mechanical right here on the roof. You see that right there? Can y'all see my cursor? Yes, you can. Perfect. Right there on the roof, that is a cooling tower. You can see a very large tower body. This looks like maybe, I don't know if it's an Evapco, but it's just one big tower fan. It's hard to tell exactly what type of tower it is, but this is a cooling tower, right? Here's your deck assembly. This is your fan assembly over on this side. That's what we're looking at. Now we see another, we got this thing right in the way. Looks like that might be another tower back over here. See, RTUs and chillers don't have a fan deck that looks like this. The only thing that has fan decks like this are cooling towers where everything's kind of offset. Or I've never seen an RTU that was large scale that had a single condenser fan for the RTU. It's just not a design I'm familiar with. So I would venture to say that this over here, if this will go away, this over here is likely a tower. It's kind of hard to see. That one could be a RTU possibly, but this over here is for sure a cooling tower. What that would tell me on this particular building is this is likely this is a water-cooled system. So they've probably got water-cooled, could be centrifugals, could be water-cooled screws. We don't know, but there's likely a water-cooled machine inside of this building. Maybe they're doing self-contained systems or water source heat pumps. Who knows? But they've got a cooling tower, and that cooling tower is a really strong indicator that this might be a building of interest to us. And this may be somebody we could go talk to as a potential customer, as an example. And so maybe you're working at a company that they're willing to start doing some chiller work, but they don't have any chiller clients. They don't know how to go get chiller clients. They don't even know where to look for chiller clients. And so I've had this happen many a times where, say, okay, well, you as the technician, if you can go find chiller accounts, they'll give you the backing as the company to own those accounts, and the company will let you go in that direction. This is the way you can do that. All right. So coming back over here, all right, we see 4 cooling towers right there on the roof. All right, so we've got another water-cooled building right here. Okay, this is the Encore Electric Delivery Headquarters. All right. Quite literally, all I did before stream was just get to this point on the map. And all I did was, stop it, all I did was zoom in. To be honest, I couldn't even tell you where I zoomed into earlier. But I'm trying to show, I didn't do anything fancy there. I'm not tricking you in what I'm showing you. I literally just picked a point on the map. I don't even know where I was. I just picked a point on the map and zoomed in, and we just started seeing things. So we're just going to come over here. All right, so we see the top of this building. Not the greatest image, but seeing what we see, there's a whole bunch of these little individual. These are all splits right here. This building has a ton of splits. That's a set of apartments, so that makes sense. Each apartment has its own system probably assigned to it. A whole rooftop, not too worried about that. That's not our forte. This looks like a large... That could be a large RTU for the building. It may be makeup water, or not makeup water, makeup air. This may be a large makeup air unit. We do see what looks like a small RTU over here. Could be a kitchen system. What is this? Victory Place. I'm assuming that's a hotel. I don't actually know. Either way, this one may not be of interest. Like if our heart, okay, here we go. Cooling towers, parking lot, or parking garage. These towers, I would assume, are feeding one of these buildings here, or maybe this building here. What is this? Oh, the Dallas Mavericks. Oh, there you go. Well, that would make sense. So the Lexus garage. So this is probably the towers for the Mavericks stadium. Let's see, does the Maverick Stadium have any other rooftop equipment? There's some exhaust fans. Yeah, those are exhaust outside air. Exhaust outside air. All right, so it looks like I would put money down. This is the garage for the state. I don't actually know. I've never been there. But I would assume this is for the stadium. This is probably a hotel that serves the stadium. These towers here are going to be for the stadium, and they'll be piped underground. In this stadium, these are almost always water-cooled. Water-cooled systems are one of the few systems that can scale large enough to service a facility like this. So I would absolutely expect it to be fully water-cooled. Let's keep on the hunt. Let's go pick here. Let's just zoom back out. Let's go pick somewhere else. Here's a clump of buildings. What do they have? So I see a warehouse district of some kind. All right, so we see little RTUs here, right? 2 fans, large body. That's all RTUs. RTUs. All right, so if you want to do RTU work, you could find those all day. That's not what we're looking for. We care about chillers. What do you have? Looks like some kind of processing facility. Okay, we see fuel trucks. We don't see any kind of cooling equipment, so that's maybe just a warehouse. I see more RTUs. And what I want to help you identify is, what does this equipment look like from the top side? All right, so we've got some small RTUs. Okay, there's your examples of some single fans, little bitty guys. And you'll see what I mean when we come across an air-cooled. These are all warehouses. All right, so here's some more cooling towers. Set of cooling towers here, set here, set here, set here. This is all chiller potential, right? So this could be cooling processes inside of the facility. This could be actual water-cooled equipment inside the facility, maybe some process chillers. These look like some more cooling towers over here. There's some little RTUs, or at least split system condensers at minimum. Let's keep looking. I want to find an air cooled. I want to show you. We're going to do this. Hopefully you get the kind of the concept of what I'm doing here, though. Like, if you don't think there's chiller opportunities where you are, look at how many cooling towers alone we found, right? That tells me there's a lot of water-cooled equipment here. Okay, this is a good example of a large RTU. We have a large condenser fan deck right here. We have our makeup air system right here, or our duct intakes, outtakes, right? So we can see this, what these hoods are doing. So I would say this is a large RTU with a lot of makeup air attached to it. You can see the same things over here on these, right? That would be my assessment just seeing that setup. But these are not chillers. Those are RTUs. This is an exhaust fan. All right. We're getting closer. I can smell one. Where are we at? We can see a whole bunch of ventilation equipment. We see what looks like maybe some duct or piping. That would be an RTU right there. This may be a water-cooled facility. Oop. Oh, it's so hard to see. Okay, that looks like ducting. That's not piping. Yeah, most of that looks like duct. What is that? Oh, it's a hospital. Okay, that's all your ventilation systems. Okay. That's why it looked like so much ventilation, because it was. What do you have? These are some very large air handlers. So this is an air handler. This is one. It's hard to tell what this equipment is. Giving air handlers of these size, it is hard to tell. It's not the blatant example I want to show you. Ooh, look at all these towers. Got some rooftop units. So here's some, these are, so, okay, let me point this out. These are air handlers. The reason I can say that, where's the condenser fans? Right? Every time we've seen an RTU, we had condenser fans. In this example, you can look at this. There is no condenser fans on this top deck. These are just air handlers. So that's one way you can quickly identify which is which. But here's the thing, being the fact these are air handlers, that likely means there's going to be chilled water equipment piping to them. The question is, where is that equipment? Let's see if we can see anything on the ground. Yeah, there's nothing obvious here. Yeah, this is actually taking a little longer than I planned on it. So that's an air handler. Again, no condenser fans. Oh wait, no, okay. Here on the side, those may be fans right there. So this may be an RTU style system. We may have a side condenser, side mounted. I'm very stubborn. I want to, here's another RTU. All right, we can see the body, we can see the condenser section. I'm very stubborn. I don't want to drag this out, but I really want to. This is, okay, here we go. What is this? This is a data center. Okay, yeah, that was going to be my guess, given the layout here. These are air-cooled chillers right here. These are all air-cooled chillers. This is what you're looking for. See, I told you I'd be successful. Question me. These are all your air-cooled chillers right here. So you'll see that the entire top deck of the chiller is just a condenser fan deck all the way across. All right, now you have to be careful because there could be some large refrigeration racks that look very similar. I would argue that these over here, how these are single line fan decks, I would argue that these over here could be just a set of refrigeration racks for some crack units. But these are air-cooled chillers. These are your chill water pipings coming in and out. That is what this whole setup right here is, sitting up on some pedestals on the roof. That's what these are over here. These are all look like air-cooled chillers. So this is what you're looking for, right? We can come over here, we can see more of them. We can see more of them over here. Heck, those may be some York machines there. You can see actually that looks like a YCIV. Looking at that fan deck assembly, we've got our, so this would be a 3-circuit machine. Circuit 1, Circuit 2, Circuit 3. Here's your control panels up here, right? That's not something you have to identify. I'm just saying that's what I'm seeing. These look like they could be some carrier machines, looking at the shape and color. These old rusted things might be Tranes. Because, you know, Trane has the stain, or the, not stainless, but the steel condenser fan blades, right? That's one of the things that you'll see common with those. These look like they could be smarts right here, to be honest. Or maybe some newer Tranes, right? These could be a newer Trane with a, well, those are only single line, right? Those may not be air-cooled chillers right here, but these for sure, very confident are. Anyway, you can kind of see the example of, if you don't think there's equipment around you, these are easy ways of going and finding those examples, right? What I did the other day at that lunch was just strictly, we pulled up a radius right there around us in close proximity, and we were able to find several chillers within a 5-minute drive from where we were sitting having lunch, right? Anyway, really, it took a lot longer than I thought I'd spend on it, but, you know, thank you, Michael. Thank you. It's all right. So this is the thing, guys. I give him so much crap on the side. You guys don't even know that it's well deserved. He gets his turn. I've been giving him crap for years. I take my title gladly. Okay, let me see if I can get back on track here. Now that I've had my fun. New name, Rabbit Hole Holden. I know. DX backup for Liebert to data center. Yeah. Tilted condensers. Oh yeah. I know what you're talking about with those Aeons. Yeah, you're right. San Antonio Airport in the cup. Yeah. Okay, let's just try to get back. Now that we've lost half of the viewership because everybody got bored, let's try to get back on track here. Oh, man. Let's see. Let me find the next question. I skipped a couple of them. About how long does it take to replace a shaft seal on a YK? Jake, shaft seals, I mean, dude, you could, a week? Because you have to, his thing, you have to recover the entire charge. You can't open that up with charge a machine. So you've got to do the recovery. You've got to do the repair, put it back together, pressure test, pull an evacuation, charge the machine, do a startup, analyze, right? So it's the full-blown process. So even though it's a shaft seal and it's a fairly simple repair, there's not a whole lot to it, it's very extensive. Like, you've got to completely take that machine down in order to safely service that circuit and get it back online. It would be cool if there was a better answer, but there's not. It's just, it is what it is. It takes several days. So however long you think it takes you. So the way I do that, here. Come on, you. Here we go. Argue with me. The way I do this, I usually schedule, this may be, typically depends on the scale, but by default, I'll go with 2 days. So day one will be recovery and staging. Recovery and then staging equipment. On a very small machine, you might get away with recovery and repair same day. Maybe. It depends. It depends on the location of your plant, everything else. So you may be able to do this repair same day. But as a precaution, I'm going to say that's just 1 day. Get the recovery done, get everything staged. We're not in a hurry. You don't want to rush this process. It's a very simple repair to then make a mistake because you're in too big a hurry. So day 2 is going to be repair. And then leak test, leak check. Get everything together. We're going to leak check it, make sure we're good. Then we're going to get it under a pressure test. All right. So day 3, we have our pressure test. We're going to make sure we pass pressure test. That means doing a standing test over at least a 24-hour period. Now, you can make arguments to cut that down to 12 hours depending on your particular conditions on site, but 24 hours is the recommended on that pressure test for a machine like this. And it could be up to 72 hours. Again, depends on your conditions, what you got in front of you. So you want to do a pressure test, and then you want to, if the pressure test holds up good, that's when you'll get into starting your evacuation. This will be where you start this overnight. Evac. And then day 4, we can, it may be another full day of evacuation. Again, this comes back to the size of the machine. So just on a basic scale, let's say evacuation did finish. So finish evac, and then standing vacuum check. So this would be something you would do at least overnight. And then day 5, maybe charge and start. charge/start. So if everything goes perfectly, you don't find anything else, you don't have any other leaks, any other issues, it's not a huge machine. Like if this was a large machine, this process would extend even further. It may take multiple days to get an evacuation down. It may take more than just the one day to do the recovery, depending on your equipment, your machine, what you have, how skilled are you at doing this process, how efficient can you be. So 5 days, if you're, again, that could easily turn into 7 if you're not careful. So, and that's without trying to rush and blow through the repair. Because that's where mistakes happen. So just from a high level there, Jake, you've got to go through this whole process to change that seal out. It is what it is, just one of those things we got to do. All right, let me catch up. Daniel, can you, if possible, briefly explain the sequence of operations on a VSD on a YVAA chiller? Let's see. I paused because I guess we would go. You're probably wanting to know the electrical sequence on the VSD. I think so. Yeah, I think we're probably asking for the electrical sequence versus the compressor. Yep. Let's get through this pretty quick. Okay. Just so everybody's on the same page, can you, if possible, briefly explain the sequence of operations on a VSD on the YVAA chiller? So this is a York air-cooled chiller, and we can get into the sequence here. So we're going to take a electrical approach to this, and from that, let's just draw the basic kind of cycle. So we come in through our disconnect. Power then feeds down into our line reactor. We'll just call it LR. This is this is filtering not only static coming into the machine, but static backfeeding back out of the VSD assembly. From there, we feed into our SCRs. So we have 3 SCRs on this machine. SCRs. And we've got 3 legs of power, so you can kind of follow through that. From the SCRs, we come out with our DC bus, so DC negative, DC positive. That's when we're going to hit our capacitors. Okay, so we've got our capacitor bank. These capacitors then feed into our IGBTs, insulated gate bipolar transistor, IGBT. Yeah, gee whiz. I'll get there, guys. IGBT. Yeah, okay, so these feed into here. We have our different IGBTs. These will be, let's see, depends on the size of these should be what, 1 module per leg on this machine. So here and here, so we've got each phase, and we've got our positive and negative bus feeding into each of those. All right. Then on the control side of it, we have the or coming out of these, we then go into the motor, right? So out of this, feed into the motor, or the compressor, however you want to look at it. And then we've got our logic board. And then we have our trigger board. That's the name. Okay, so each of these serves kind of a different purpose, but the logic board is the main brain that talks back to the micro panel or the control panel for the chiller as a whole, and it is coordinating all of these different components together in sequence. So we come in main power from disconnect, we process through our line reactor, we hit our SCRs. Those go from AC to DC, so we have an AC sign, and then so these are rectifying the circuit into our capacitor bank, and then into our IGBTs, which act as our inverters. Our inverters are then taking this DC, turning it back into a modulated AC power, which then our motor is able to run off of the hertz these IGBTs are able to create. And so these work in unison together based off of the logic and trigger boards. So the trigger boards are activating the gates in the SCRs, and they also connect to the IGBTs. So there's a whole harness assembly that comes off of these and goes to these components and fires them accordingly. And all of that is coordinated through the logic controller. The logic controller, or the logic board, is also responsible for monitoring safeties, current conditions, and is communicating all of this back and forth via a data bus. So it's a network or computer talk back and forth between the main control board and the VSD control board, which we call the logic board. So they're sending signals back and forth. Now there are some hard safeties that run to the logic board, like your high pressure safety, your what they call, is it the K1 safety, or that may be on the larger. Yeah, no, the smaller ones should have a K1 relay as well. Either way, there's a set of safety switches in here that are monitoring for like a high pressure condition. Those can trip out and cause the signal to drop out. But for all intents and purposes, this is where all the thinking happens for this drive. So we have power sent to here in terms of our sequence. We have power sent to here. The drive is going to get a command to turn a compressor on. Now this drive there's multiple compressors attached to this with different sets of IGBTs that feed those compressors, so keep that in mind. But the logic board is going to receive a signal from the main control board. We need to turn a compressor on to make leaving water set point. So the logic board is then going to make sure that all the safety checks are good. It's happy with the condition that the chiller is in. Then it will activate the SCRs. The SCRs are going to charge the capacitor bank. So these should, from a standing still position, these should be discharged. So we've got a set of bleed resistors that accomplish that. So they shouldn't be holding power. So we have to charge this bank to get it ready to run and feed the IGBT's DC power. So these activate, charge the bank. That takes a couple of seconds. Usually there's a status that shows up on the display that just explains, hey, we're in a DC bus charging state. Once the bus is registered as charged, ready to go, we can then start triggering the IGBTs to send an output. Now the logic board is monitoring motor current. It's monitoring for ground faults. It's looking at the different safety parameters on where it needs to be, and the main control board is telling the logic board where in the staging it needs to be. So depending on what our leaving water temperature is compared to set point, if the chiller only needs this compressor at 80%, it's telling the logic board, okay, you need to be at 80%. So upon initial startup for this machine, the logic board is only going to bring the compressor up to its minimum hertz, which I think is 50 hertz. These are 200 hertz motors, as long as I'm not getting that confused. And 50 hertz is the minimum that these will come online to. So first they'll come on, it'll get stable, make sure all the readings are good, it's still happy, our current's good, our pressures are good, water temperatures are good, all that's, it's happy, right? It'll start to stage on condenser fans accordingly. After a minute or two, it will then begin to stage up the actual compressor. And so that's where the logic board will start to respond to the main control board of, okay, I want you to be at that 80% state. So it will start to increase the output to the compressor motor, the hertz output, by triggering these IGBTs in a proper sequence with each other. So then it will stage up, and let's say we get to set point and we no longer want 80% on the motor. Maybe we only want 70%. So that logic board will get that communication from the main board. It will then start to back that motor down and keeping this whole sequence in sync with itself. So the SCRs through this whole time are just staying, like, they're triggered open and they're flowing through them to feed the DC bus and keep power to the IGBTs. The trigger board is keeping the gates engaged. The logic board is keeping everything in sequence. And we're just going to modulate up and down. At some point, we need to shut down, whether it be via a safety got tripped, whether it be via a we just lost our occupation call, right? So the building is ready to shut down for the evening or something to that effect. Essentially the chiller, the control panel will begin to stage down and tell the logic board, hey, I want you to ramp down, let's get to a minimum, come down gently, let's get to a stable state, and then I will stop the call to you and tell you to shut off the circuit, and just completely shut the compressors off at that point. And then once the compressors shut off, it does that by telling these gates to stop outputting. The IGBTs stop outputting, the motor shuts off, and then the trigger board will kill the SCR gate signal. So these will turn off and they'll stop passing power through them, and then the bleed resistors will do their job in bleeding this capacitor bank down and getting this back down to a 0 volts DC. So that's your basic electrical sequence from startup to shutdown and kind of in between on a really high level for how these drives are functioning. Yeah. As I said, there will be multiple sets of these IGBTs, just depending on the size of the machine for each compressor, right? So usually you'll have, on an upper deck assembly, you'll have one set for one compressor, then a lower deck assembly will be another set, but it's all part of the same drive assembly. So they're feeding off the same DC bus, the same capacitors. We've got the same SCRs feeding in. We just got 2 layers to the IGBTs. Yeah. Our centrifugal, water cool, chiller York. Why liquid level set point not achieved? Alarm come. Just one second, Jesus. Now, let's see, Zara. In terms of connecting with me through the academy, one of the easiest, so there's 2 easy ways, right? You can either, if you're enrolled in the service program or the certification program, you can go to the community page, post what you need to in there, share videos, the whole bit, and I can get in there and see it, and we can talk through it as a community with everybody in the programs and discuss the issue. Or you can just send me an email at hvactime at hvactimetx.com. Sending me an email there. I try my best to keep up with it. I do have to prioritize those responses as best I can. There's a lot of traffic that flows through there in a day, but yeah, those are the two primary ways to reach out, get in touch, and go from there. Okay, liquid level set point not achieved, alarm come. Yeah, so that would indicate to me you have probably a York YK. It doesn't have to be a YK. This could be a the YMC, the YZ, the YK. They all kind of use the same basic control sequence for the liquid level. But what you'll see is you'll get a subcooler seal loss alarm when the liquid level gets below a certain point, and you're not maintaining a high enough refrigerant, what they call refrigerant effectiveness, I think. Here, we can actually pull one up. Let's come here. And then let's go, let me pull up one of the display panels. Should be right here. Let's see, does this tell us the subcooled temperature, drop leg, pump, refrigerant, temperature? You know, this one doesn't show us the effectiveness. Let's let me find a different one. Let me find one that actually shows the liquid level screen. I think this one. Ramp, liquid, position, target, drop leg. Okay, so it's basing it off of this subcooling temperature, right? And yeah, but this isn't the actual. I'm pretty sure there's an effectiveness value that without spending a ton of time digging for it, I know I've got a copy of this screen, but either way, we're trying to control liquid level in the condenser. That's how these machines operate, off of subcooling for refrigerant effectiveness. So it's different than what I explained early in the stream with Trane, where we're using an economizer. In this case, we're using subcooling. So if our subcooling is low, then we're going to have issues maintaining effectiveness on the refrigerant going into the evaporator. It's going to cause different issues. You're going to see this through the sight glass. So typically we want our sight glass to be about 1/3 to 1/2 glass on these machines typically, which is about 1/2 to 1 inch above the subcooler rack assembly. In the bottom you can see the steel plate that sits over that rack if you look inside through the sight glass with a flashlight. So we want to be up above that plate high enough. So not achieving that, so there could be a couple of things, right? So there's a metering device right here. Well, this particular one shows it down low. It could be up higher coming into the evaporator. Either way, it is a type of variable orifice. It'll look like a butterfly valve from the outside with an actuator, but it's a variable orifice. That's how we refer to them. So this orifice can change position just like a butterfly valve. It's the same basic operation, and that's how we're able to control refrigerant flow. Sometimes those actuators go bad, so you may be a case where you need to troubleshoot the actuator. There may be an issue with the valve itself. You may be out of calibration on the actual liquid level sensor, which there's an entire process for that, or maybe that sensor is just bad and you need to replace it. Either way, these are the main things that I'm looking at when I am having trouble maintaining liquid level in the condenser, because when these machines work correctly, even if we're having a low charge issue, what they should do is they should favor stacking in the condenser, and they're going to starve the evaporator. That's what the condition you'll see with an undercharge if everything is working correctly. You're going to see really low levels in the evaporator, but your condenser is going to look fine. If you're not seeing that, then one of these components may be the source of your problem. Excuse me. So this is what I would want to dive into. The valve and the liquid level sensor itself. And you can use the sight glass as a means of being able to physically see these levels change and adjust, and try to kind of use that to tune your troubleshooting process. And whenever this runs, so once you get above a certain load percentage, that liquid seal, subcool seal loss fault that'll show up here, or that not fault, but a warning that'll show up here, will go away. But once you get down below I think it's a specific RLA. I don't know if it's 60%, 70%, something like that. If we get down below a certain load value on the motor, then it triggers that we need to maintain a high enough subcool temperature, which means we need a high enough liquid level to maintain that subcooler seal so that we have proper efficiency on the machine. And if we get down below that, then we'll have that fault trigger up here. And that, again, that's just where you dive into what is the sight glass level, what is it actually showing you. If your sight glass is, say, 1/3 or higher, but you're showing really low liquid levels according to the sensor down here, it's probably a sensor issue, because once you're up into the sight glass that high, you should not be reading really low refrigerant level positions at all. If you are down below that sight glass and you show low positions, like it could be just a valve issue. You may have an issue with your valve, whether it's not calibrated correctly, whether it's not, whether the actuator went bad, something along those lines is probably causing it to hang up, and that's what's giving you trouble. So that's what I would be diving into in your case. Is these are the two components that control liquid level in the condenser. Why are we not maintaining level? And if both sight glasses are so low that neither of them have liquid level in them, that's a major concern, right? That's where you get into, okay, we've lost way too much refrigerant. In most cases, if you actually have really low liquid level in the condenser, then you're going to see really high liquid levels in the evaporator, and that's that trade-off you're going to be looking for. So if you think that's going to be an issue, not only look at the sight glass on the condenser, but look at the evaporator and compare them. And be careful that you don't, just because it looks clear, don't get tripped up that one of them may be higher than the other. So you may have a liquid level above the sight glass, which at that case, don't let that fool you into thinking that you've got lots of refrigerant in there. You might actually be, or you don't have enough, that you're really low on refrigerant, because it may be the fact that you just have so much stacked in one or the other that is causing, it looks clear. It looks like there's not liquid level in it. It's really just really high. So it's something to be just very cautious of if you're not used to seeing those. Like there's a tint difference. There's different, like you can see as you gain experience, you'll begin to recognize the patterns of what a full sight glass looks like compared to a empty one, and you can tell the difference with time. That does become kind of a challenge to do when you're early on, and being able to tell the difference sometimes. So just look really, really carefully and don't let that trip you up. All right. I do see, we're right at time. My EXV starts working, suction pressure opening. Starts working, suction pressure, EXV opening 100%, discharge superheat is low, discharge or below target, suction superheat flooding, gas charge is perfect, Flow is perfect in this case. I'll find this is because of non-standard chiller model. Okay, so we've got a aftermarket EXV program. Set point in program is required. Please explain. So Tejas, there's a lot of important information we don't have in this post. You say it's after. If I'm reading this correctly, I think you're saying it's an aftermarket valve and controls. I don't know what control panel you're working with, so that would be an important piece I'd need to know. There's a lot to this. If you would, Tejas, send me an email. I'm going to add my email to the chat here. That way everybody has it. And we can talk about it further there and maybe even do a follow-up on the next stream to discuss it potentially. So yeah, feel free to send me an email at that address, and then we will. I can follow up further from there, because there's just not quite enough information to really give you how you're going to fix it, right? You can definitely see that, okay, you're flooding back. All right, got that. But there's, what temperature sensors do we have? Okay, we got a Corel Pico 5 with Corel EXV. Well, it's probably a Dan Foster Sporlan EXV, but yeah, let's follow up on the side, bud. With that, I do need to wrap this up today. I really appreciate everybody's time. MTT, make the time for your family, for your spouse, for your kids. We're wrapping up busy season. We're going into, at least for the northern hemisphere, we're going into our more chill season, I'll say. I'm not going to say slow season because we don't really have those. But I know everybody on the south of the equator, your season's getting ready to fire up. I've got some international trips pending that I'm going to be looking at having soon, so I'll be down during what my winters, y'all summer, so I'll be down there with some of you guys, kind of helping work through some of those systems. So that'll be fun. Looking forward to those. Getting to expand this on an international scale is always a fun thing. And yeah, really appreciate everybody's time. Have a great rest of your week. I expect to see y'all next week, unless, life does its thing. So I make plans all the time and it kicks me in the teeth. So I kind of, anyway, have a great